chaotic phenomena related to ground states of disordered systems have been predicted by physicists since the 1980s. The first rigorous evidence of chaos was discovered by Sourav Chatterjee about 15 years ago. An interesting aspect of Chatterjee's work was that it revealed an equivalence between a chaotic behavior of ground states and anomalous fluctuations of the ground state energy of certain Gaussian disordered systems. Our aim has been to show that Chatterjee's results give evidence of a more general principle. By establishing an analogous connection between fluctuations on one hand and chaos on the other in the context of first passage percolation. Let f be some probability distribution on the positive axis and assigned independently to the edges of the integer lattice, here depicted in 2 dimensions, independent variables omega, omega prime, with distribution f, and a uniform 0,1 random variable u. For each t in the interval 0,1, we define a new configuration omega t, which takes the value omega if t is less than u, and omega prime if t is larger than or equal to u. For each t, this gives a weight configuration on the lattice, and as t goes from 0 to 1, the weights flip from omega to omega prime. For each t, the weights induce a metric on the integer lattice where the distance between 2 points u and v is the infimum of the weight sum you pick up along any path from u to v. Let pi t denote the geodesic, that is, the distance minimizing path between u and v in this metric. If not unique, then we let pi t denote the intersection of all such paths. Chatterjee's work suggests a connection between fluctuations of the distance between 2 points and the overlap between the geodesic between those 2 points at different time points, as the following formula shows. From this formula, a straightforward calculation shows that a sublinear variance growth is equivalent to a sublinear growth of the overlap between these two geodesics for a fixed t. First passage percolation is known to exhibit sublinear variance growth, hence establishing the equation above would imply a chaotic behavior of geodesics in the sense that the expected overlap would grow sublinearly. In the paper, we established the variance formula and hence a sublinear overlap of the geodesics in the case of integer-valued weight distributions. For continuous weight distributions, we establish a version of the variance formula with an extra error term, which is nevertheless sufficient to establish a chaotic behavior of geodesics in first passage percolation in this sense. That is, if you depict the geodesic between two distant points at two different time points, then they are practically disjoint. Chaos has previously been established in spatial growth models in the work of Ganguly and Hammond. They study a model known as Brownian last passage percolation, which in the 2D setting is known to belong to the KPC class of universality. In last passage percolation models, one aims to maximize the weight picked up along directed upright paths of an n by n square. In their setting, they obtain remarkably precise results, showing that the transition from stability to chaos occurs at time n to the minus 1/3. We extend the easy part of their work and show that in last passage percolation with more general weight distributions, the transition from stability to chaos occurs at time 1/n times the variance of t, which in the exactly solvable setting corresponds to precisely n⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻